Hey Mr. League or anyone else that's watching this video, this is my project on non-Euclidean geometry. So before we understand non-Euclidean geometry, we have to understand what Euclidean geometry is and where it came from. So Euclidean geometry is the mathematical laws, concepts, and foundation that was laid by Euclid, a man that we know very little about. Although we do know that he wrote a book called The Elements, which is a phenomenal work of mathematical literature that explains all five of Euclid's postulates or axioms in a method which proved every postulate with only the definitions of work Euclid had already stated within the work. So technically speaking, Euclidean geometry is composed of two-dimensional and three-dimensional geometry that stays consistent with Euclid's postulates and work. So if we take a closer look at Euclid's fifth postulate, which is called the parallel postulate, it states that two lines crossed by a third would be parallel if their respective interior angles had a sum of 180 degrees. And if they did not add up to 180 degrees, then the lines would intersect at some point. And if we look at figure 2, this is just Euclid's postulate visualized. It makes a lot of sense and it's pretty simple to look at today. But the problem was that it could not be proven. And this confused every mathematician, including Euclid, from Euclid's time all the way to the 1800s. So now that we understand the confusion and problem with Euclid's fifth postulate and the parameters of Euclidean geometry, we can sort of understand what non-Euclidean geometry is. And the creation of the two forms of non-Euclidean geometry sprouted from the confusion around Euclid's fifth axiom. The first of the two forms of non-Euclidean geometry that was discovered was by Theodosius in 200 BCE. He discovered spherical or elliptic geometry. This was formally introduced or proposed in 1854 by Bernard Riemann. Slightly before Riemann's time, hyperbolic geometry was first proposed by Nikolai I. Lobachevsky in 1829. Technically speaking, non-Euclidean geometry is defined by the lack of existence of parallel lines as shown in figure 3. This means that non-Euclidean geometry respects Euclid's first four postulates, but retains their own version of the fifth. So if we look at spherical geometry and its fifth postulate, or its version of the fifth postulate, as Eric Weisstein states, through any point in the plane, there exists no lines parallel to the given line, which is just saying that there is no concept of parallel lines in any form of non-Euclidean geometry, which includes spherical and hyperbolic. So if we look at figure 4 and we look at the line segment A, you can see a little bit of a curve exhibited in the line. And this is because all lines of spherical geometry retain what is called a positive curvature. And you'll also notice that there's actually two right angles on this triangle. And that's because in spherical geometry, the sum of angles of triangles is always greater than 180 degrees. So if you actually look at the triangle on the right-hand side, and it shows what we would consider a normal triangle or a triangle that obeys Euclid's principles, it's actually only an estimate because since it's on a spherical surface, spherical geometry is required to calculate the exact distance and angles. Figure 5 just further cements the fifth postulate and how all lines intersect. And you can actually sort of imagine figure 5 on figure 4 using latitude and longitude to construct the triangle of figure 4. In hyperbolic geometry, it shares the same fifth postulate as stated earlier, although this actually is almost the opposite of spherical geometry because it exhibits a negative curvature as shown in figure 6. Additionally, the triangles of hyperbolic geometry have angles that add up to less than 180 degrees, which again is contrary to spherical geometry. But what is the application of non-Euclidean geometry? So if we look at Einstein's general theory of relativity, as shown in figure 8 somewhat, the bending of four-dimensional space-time fabric around massive celestial bodies is dependent on, their mass. And to calculate the differences in their mass and the differences that they exhibit on the space-time around them, we astrophysicists have to use non-Euclidean geometry. Although we do not know what is best applicable to the universe, because we have to understand the shape of the universe in the fourth dimension, which is extremely difficult for the human mind. But if we look on a much simpler and smaller scale on Earth, and pilots and ship navigators, they use spherical geometry because the Earth is apparently round. And if you look at figure 9, this is much shorter than this path is much shorter than a straight line, or what we would consider a straight line, between Canada and Germany. So thank you very much for listening, and stick around for the disclaimers.